Hey everyone, let's kick off with something simple and relatable. Have you ever rolled a ball down a ramp? What happens? It speeds up, right? But what exactly is happening? Well, the ball is gaining kinetic energy as it moves. But what exactly does that mean? In physics, kinetic energy is the energy that an object has due to its motion. Everything that's moving has kinetic energy, from the tiniest dust particles to the fastest cars. The faster something moves, the more energy it has. Here's the formula that tells us exactly how much energy an object has based on its mass and speed. Kinetic energy equals 1/2 multiplied by mass multiplied by velocity squared. Let me break it down. K represents kinetic energy, m is the mass of the object, in kilograms, v is the velocity of the object, in meters per second. So, the faster the object moves and the more massive it is, the greater its kinetic energy. Think about a car and a bicycle. The car, being heavier and faster, has way more kinetic energy than a bicycle. Alright, now let's focus on speed. It's not just about how fast something is moving. Speed actually has a huge effect on kinetic energy. Take a look at the formula again. Kinetic energy equals 1/2 times mass times velocity squared. Notice the velocity is squared. This means that doubling the speed of an object doesn't just double its energy, it quadruples it. So, let's say you're driving a car. If you go from 20 meters per second to 40 meters per second, your kinetic energy doesn't just double, it quadruples. That's why fast-moving objects like race cars or bullets have so much more energy than something moving slowly. Imagine you're running a race and you start slow, but the moment you sprint, you gain a lot more energy. The faster you go, the more energy you have, and it happens much quicker than you might expect. Now, let's talk about mass. The mass of an object also plays a crucial role in how much kinetic energy it has. Back to the formula again, kinetic energy equals 1/2 times mass times velocity squared. Notice how mass is a part of the equation. This means that heavier objects have more kinetic energy for the same speed. Let's think about it this way. Imagine a small car and a huge truck moving at the same speed. The truck, being heavier, has more kinetic energy than the small car. It's like comparing a bicycle and a massive truck. Even if the bike is fast, the truck's bigger mass gives it much more energy. So, if you're a heavy object moving fast, you've got tons of energy stored in motion. Mass matters. Now, let's take this a step further and talk about how kinetic energy shows up in our daily lives. From the moment you wake up and start moving, you're dealing with kinetic energy. Here are a few real-world examples. A rolling ball. When you roll a ball down a ramp, it speeds up, gaining kinetic energy as it rolls. A speeding car. The car's engine burns fuel to move, converting that energy into kinetic energy as it drives down the road. A flying bird. When a bird takes off, its wings generate enough kinetic energy to lift it into the air and help it soar. Rivers and streams. The fast-moving water has kinetic energy that's used to generate hydroelectric power. In fact, waterfalls convert gravitational potential energy into kinetic energy. So, whenever something moves, it's carrying kinetic energy. From tiny particles to massive objects, kinetic energy is always in motion. Okay, let's talk about kinetic energy during collisions. This is where it gets really interesting. When objects collide, their kinetic energy doesn't just disappear. It can be transferred or even converted into other forms of energy, like heat or sound. In an elastic collision, like two billiard balls bouncing off each other, kinetic energy is conserved. That means the total kinetic energy before and after the collision stays the same. But in inelastic collisions, like when a car crashes, some of the kinetic energy is lost. It turns into heat, sound, and the deformation of the objects. It's like when you throw a rubber ball against a wall, it bounces back with almost all of its energy. But if you drop a clay ball, it squashes and loses energy to heat and sound. Kinetic energy doesn't just vanish, it changes form. Let's wrap up with an advanced example. Imagine you have a 50-gram bullet moving at a speed of 200 meters per second. What is its kinetic energy? We use the formula kinetic energy equals 1/2 times mass times velocity squared. First, we need to convert the mass from grams to kilograms because the standard unit of mass is kilograms. Mass equals 50 grams equals 0.05 kilograms. Now, let's substitute the values into the formula. Kinetic energy equals 1/2 times 0.05 kilograms times 200 meters per second squared. Simplifying this, we get kinetic energy equals 0.025 times 40,000, which equals 1,000 joules. So, the kinetic energy of the bullet is 1,000 joules. That's quite a bit of energy packed into a small object, and it's a good reminder of just how much energy is stored in motion. So, here's what we've learned today. Kinetic energy is the energy an object has due to its motion. It depends on two factors, its mass and velocity. We saw that velocity has a huge effect on kinetic energy because it's squared in the formula, and doubling your speed means you quadruple your energy. We also learned how kinetic energy applies in the real world, from rolling balls to speeding cars. And finally, we saw how collisions affect kinetic energy, whether it's conserved or transformed into other energy forms. So, whether it's a race car, a falling rock, or a moving spaceship, kinetic energy is at work, driving motion all around us. I hope this explanation helps you understand how kinetic energy works in the world. I'll see you next time with another exciting concept of physics.